Okay, so it's my pleasure to welcome Weihong Xu from Virginia Tech. She'll talk today about quantum K-theory of partial flight varieties.
Thanks a lot for the invitation, and yeah, it's my great pleasure to be here. If anything is not clear during the talk, please feel free to interrupt at any time. Okay, so first of all, I'd like to give a brief review of K-theory and just to set up some notations. So let X be a projective variety over the complex numbers. And then the K-theory of X is going to be the free abelian group generated by vector bundles over X modulo the equivalence relation given by short exact sequences. And the product is just the tensor product of vector bundles. Moreover, whenever you have a short exact sequence of vector bundles, we have the following Whitney relations that says the lambda y class of E is equal to the lambda y class of E prime times the lambda y class of E double prime, where lambda y of E is this formal polynomial in Y. And you can think of it as the K-theoretic analog of the total term class. And so if X is smooth, well, soon we will be restricting our attention to the case where X is a partial flat variety, and this is smooth. But more generally, if X is smooth, then every coherent sheaf has a finite resolution by vector bundles. And then the coherent sheaves also live in the K-theory ring as this alternating sum of vector bundles. And this does not depend on the choice of the resolution. And for example, so the case we're most interested in is if you have a subvariety of X, then its structure sheaf is going to be a coherent sheaf, and it'll live in the K-theory of X. And if you just consider the structure morphism, then that makes the K-theory of X an algebra over the K-theory of a point. If you just pull back, vector bundles, and the K-theory of a point can be identified with the integers. So for the flag variety, we have a Z basis of the K-theory given by structure sheaves of Schubert varieties. So here, OU is short for structure sheaf of the Schubert variety XU. And on this flat variety, so now X is just equal to the flat variety. We have a torus action, which scales the coordinates of Cn. And we often consider equivariant K-theory. So here we just consider equivariant vector bundles, and everything I've said can be made equivariant. So this works if we have a short exact sequence of equivariant vector bundles, and if omega is a T-invariant subvariety, then its structure sheaf will have a finite resolution by equivariant vector bundles. And here, the equivariant K-theory of a point becomes the representation ring of T.
Mm-hmm.
So over X, we have this sequence of tautological vector bundles. Where the rank of Si is Ri. And we can write the following presentation for the K-theory of X, called the Whitney presentation. Where the generators are wedges of the tautological bundles and their successive quotients. And the relations are Whitney relations of this form. So, yeah, any questions so far before I move on to quantum K-theory? Okay, so now let's talk about what is quantum K-theory. So this was introduced by Given, Tao, and Li around the 2000s, and I will only talk about the small quantum K-theory, and in the case of a flag variety. So so this quantum K-theory is going to be a deformation of the ordinary K-theory. And additively, it's just equal to the ordinary K-theory tensored with a formal power series ring. And for our flag variety, we're going to have k of these Navico variables. And there is an associative product denoted by star. It's defined using K-theoretic Gromov-Wheaton invariants, which I will introduce next. So each of these K-theoretic Gromov-Witten invariant is associated to a couple of K-theory classes. So here, sigma are in the K-theory of X, and an effective degree D. For the flat variety, it's just going to be a K-tuple of non-negative integers. And it involves the moduli space MD, which is short for M03XD bar. Well, this is just a compactification of the set of maps from P1 to X, such that the push forward of the fundamental class of P1 is equal to D. So this just means if you take the K Schubert divisors in the flat variety X and you count the number of pre-images of each, well, if you put the Schubert divisors in general position and you count the number of pre-images, then you're going to get this tuple of integers. Yeah, and on the boundary, you get degenerate maps whose domain is a tree of P1s. Okay, so so over here, from this moduli space MD, you have three evaluation maps to the flag variety X. In the interior, it's just given by evaluating your F at 0, 1, and infinity on P1. So finally we can write down the definition. So here you're going to pull back these sigmas via the evaluation maps, multiply them in the K-theory of MD, and then you're going to push forward to a point. So this lands in the K-theory of a point. So in general, the definition is more involved, but for flat varieties, we don't need to worry about virtual classes, so we can just write it in this way. So if you've seen cohomological Gromov-Witten invariants, one difference is that these do not vanish for dimension reasons. Okay. So we have seen that we have the Schubert basis. And that can be carried over to quantum K theory. So if we multiply two Schubert classes in quantum K theory, we can then expand as a linear combination of Schubert classes with some Qs. And by definition, these structure constants are related to the K-theoretic Gromov-Witten invariants by the following recursive formula. So this is going to equal here this OW check is the K-theory class dual to OW. Oh, sorry, I think these are supposed to be, I've been writing them, yeah, they're supposed to be, just to be consistent. Okay, so this, this class is dual to OW in the sense that this pairing is equal to this delta function. So it's just the dual basis in ordinary K theory. Is there any questions?
Yeah, I just forgot the small versus big quantum cohomology. If you're taking, you said the small quantum cohomology, I was wondering if you would be interested in doing like understanding big quantum cohomology, what additional classes do you need to insert in this moduli space?
Right. So right now I only have 3-point invariance. If you want to do big quantum, you have like arbitrary number of insertions.
Okay.
Do you know of any simple explanation or any why one needs this recursive formula as opposed to we don't have that in cohomology, for example?
I guess to make it associative.
But I mean you're right. But you don't know why that's.
I think there should be a geometric explanation too, but I don't think I can give it right now.
Yeah, one comment about that is when you curve breaking into two pieces, this cohomology class is the sum of the two pieces. With a structure shift in K theory, it's like structure shift of one piece, the other piece, but there is also structure shift of the intersection. That's a correction term, which produces this.
Thanks. So, so from the definition, it's not clear. So from this definition, that that expansion could be a power series in Q. But it was proved that for G mod P, that it will actually be a polynomial. So this was proved by Anderson, Chen, and Zhang. For G mod P. In some special cases, it was proved by other people earlier. And moreover, so even though those structure constants themselves do not have an enumerative interpretation, they still behave like enumerative invariants in the sense that they are conjectured to be positive. By positive, I mean they alternate with the codimension. Their signs alternate with codimension, and we can make it equivariant as well. So the precise statement is like this. So here the sign is basically measuring codimension. This term comes up in the dimension of the moduli space. And here this is the, so epsilon I is the character that picks up the ith coordinate of the torus. And so this, and C of some alpha is the one-dimensional representation associated to alpha. So this lives in the K-theory of a point, equivariant K-theory of a point. And the conjecture says that this only, as a polynomial in these, only involves coefficients in the natural numbers. So it generalizes the equivariant positivity in the non-quantum case. So if you set the D to 0, then you recover the positivity, equivariant positivity in the non-quantum case, which has been proved, and I think Professor Graham did some work related to this as well. And various people conjectured this. I'm not sure who exactly to attribute to. Okay. So we are interested in how getting a presentation for the quantum K-theory of the partial flag variety. And we are particularly interested in one that deforms the Whitney presentation, which I wrote down earlier. And our main conjecture is the following. This is joined with Buch and Mihalcea, Sharpe, Zhang, and Zhang. So we conjecture that in the equivariant quantum K-theory of the flag variety, the Whitney relations become so when you set the Q's to 0, you recover this part, which is the classical Whitney relation. And we also prove that if these relations hold, then they form a complete set of relations in the sense that you get a presentation by generators, and the ideal of relations is generated by these. So before we made this conjecture, these were first proved for Grassmannians. So for Grassmannians, this has been proved by a subset of my collaborators. So this is 23. And we also prove it in the new case of FL1 n-1 n. Yeah, so this this is a new case that we prove. And by the way, so Gu, Sharpe, Zhang, and Zhou are all physicists. And we were able to come up with this conjecture because of some inspiration from physics, which I wrote over there in the example of FL3. For the physicists, they realize these flag varieties as GLSM, and they wrote down this so-called twisted superpotential, and in this case, it looks like this expression of logs and dilogs, and then the relations come from taking the critical locus of the superpotential in this way. And then you can actually compute it, it's not too bad. And after that, you get some equations that are not symmetric in the variables. And so you symmetrize them in some way. And after that, so you're going to symmetrize, and then you're going to interpret the elementary symmetric polynomials in the variables as wedges of your tautological bundles. And then that will give you exactly these relations. And the T here is the equivariant, is an equivariant parameter.
But you're thinking of W as just a formal expression of these variables.
Yeah, so basically so for the physicists, the x's are some like fields, but for us, they are k-theoretic term roots. So if we make this dictionary, then somehow it works, but it still remains mysterious to me. So actually, I think the case of these incidence varieties is a bit simpler than the Grassmannian case, and our proof is more direct. The proof uses the following formula that I proved earlier. So for these incidence varieties, we have that these k-theoretic Gromov-Witten invariants, if one insertion is a determinantal line bundle, then you either get 0, this is the case if di is positive, or you get this classical invariant. Where this gamma d is given by pulling back and pushing forward via two different evaluation maps from the moduli space MD, and it lives in just the K theory of X. So this computation happens in the K theory of X, and if sigma and tau are Schubert classes, then the tau of D is going to again be a Schubert class, and this is computable. Although we don't need to compute it. In the proof, we just need to use that we have a formula of this form.
So is I either 1 or n minus 1 here?
No, oh, yeah, I is either 1 or n minus 1, yeah, exactly. Well, this formula is in fact conjectured by Buch and Mihalcea for all partial flag varieties. And they also proved it in the Grassmannian case. Well, they proved something more, but this is a consequence. And it might be and it might be more general than a type A thing. It also works for all co-minuscule flag varieties, but I don't think it works for all Gmod P's. And it can be viewed as a quantum K divisor axiom. So in quantum cohomology, we always have the divisor axiom, which says that if you want to compute a Gromov-Witten invariance where one insertion is a divisor, then you can reduce the number of insertions by 1. So here, this conjecture is equivalent to the following. Yeah, so you see that your 3-point invariant is equal to 2-point invariant. And so here you, the OSI is the class of the ith Schubert divisor. And moreover, for the complete flag variety, we can show that this quantum K divisor axiom implies our conjectured Whitney presentation. So next I want to say a little bit more about the geometry of this divisor axiom and some other consequences of it. So,
so you said can the class gamma of D be calculated, or tau of D be calculated? I couldn't remember.
Yeah. For if gamma is a Schubert class, then this is going to be a Schubert class, and you can calculate it combinatorially.
In K theory, it's a Schubert class as well.
Yeah, it's the structure sheaf. It's going to be a structure sheaf of the curved neighborhood, which is again a Schubert variety. Yeah, so it's going to be, so if you have a Schubert variety, and then you're just looking at like the closure of all the degree D curves passing through this Schubert variety, and that's going to, again, be a Schubert variety, and you're taking its structure sheaf. So geometrically, to if you want to prove this divisor axiom, it suffices to prove the following. So so here you're taking the Schubert divisor and a Schubert variety, and these two are in general position, and then you're taking this intersection, you're pulling back by the evaluation maps and taking the intersection in your modular space. This is the left-hand side. And the right-hand side is just and then you're just going to send it via EV3. So you're going to land in your X. And so pictorially, you're just looking at all the. So you're looking at the degree D maps from P1 to your X, where that passes, so the image have to pass through on both the Schubert divisor and the Schubert variety, and here you're looking at the union of all these curves in X, and you're taking the closure. That's the space on the right. Okay. So the thing you want to prove is that the general fiber of this map is rationally connected. So this is a condition that guarantees the higher push forwards would vanish, and then you can sort of get the formula by using the projection formula. And this is what I did in the case of incidence varieties. And in the case of incidence variety, not only was this divisor axiom helpful for getting a presentation, I was also able to use it to get some closed formulas, like some Schubert calculus-like formulas in quantum K theory. So for these, I have closed formulas for multiplying a Schubert divisor class with an arbitrary Schubert class in equivariant quantum K-theory. And non-equivariantly, I have Littlewood-Richardson rule, which computes the product of arbitrary Schubert classes. So to write down these formula, let me introduce some notations. So now X is this incidence variety. Schubert varieties in X are actually indexed by the roots of type AN-1. Okay, so this is all the roots of type AN-1, and well, like maybe more often you think of Schubert varieties as indexed by permutations. Well, so each one of these also correspond to the permutation such that it sends 1 to I, n to j, and it's the minimal such permutation. I learned from Nicolas Behren that this doesn't only work for type A. So in general, if you have adjoint Gmod P's, then the Schubert varieties are going to be indexed by long roots. And if you have coadjoint Gmod P's, then they are going to be indexed by short roots. And this is exactly the this is both adjoint and coadjoint, and in type A you just get these. And in general, they can be determined by a Dinkin diagram and a choice of adjoint or coadjoint weight. So, so for I is not equal to j, I'm just going to write Oij. So Oij is going to be the structure sheaf of the Schubert variety if Ij are within bounds. And I'm going to extend the notation so that if I is too big, then we factor out a Q1, and if j is too small, we factor out a Q2. And these and the formulas I'm going to write down can be so some of them can be seen pictorially. So
does this get iterated? Like if I is really big, you could get some power of Q1?
Yeah, it just gets iterated. Although the only powers, the highest powers that appear in this. So if you start with, if we start with honest Schubert classes, then the highest power you are going to get is actually just Q1 times Q2. But you could start with something that already with Q in it, and the formula still works. Okay, so here let me draw the draw the roots of type A3. So each of them is a dot. So this is 1, 4, 2, 4, 3, 4, 1, 3, 1, 2, 2, 3. So these are positive roots.
Sorry, 3, 4.
Oh, sorry, 3, 4. Yes,
Okay.
thank you. Okay, and then you have negative roots. Okay, and so on. So so then when you multiply with the first Schubert class, what you're going to be getting is you're kind of going maybe a different color. So you are just going left like this. So maybe it'll make more sense when I write down the formula in a minute. But when you get to the simple roots, what's going to happen is you will be getting more terms when you start with the simple root. And everything I draw is this. So far, these are the same as in classical K theory, but the quantum in quantum K theory, you also go out. So if you start here and you multiply by your divisor, you're going to get out, and so this is going to be 5, 4. And if you start here, you're going to get 3 things like this. Yeah, and if you start here, you're going to the left. So you can complete this. Yeah, you can. So and if you multiply with the other Schubert divisor, you're just going right, and it's symmetric. And you can think of these maybe as affine roots. Right, so now let me write the formula. Or maybe I should maybe stop soon. Okay, I guess I can also stop. So this is this is what the formula looks like. Okay. Thanks.
At the very bottom, you have that that red one, but you don't have the other red, the orange ones, like at the like at the very.
Oh,
like down from from the 4-3, there's this one going down.
Oh, this one?
Yeah,
it just goes out. It also goes.
But in the orange, but you would think that if the picture were the same, you get those like from the 3-2, you get an orange one going down also.
Oh, 3-2. Yeah. It also, I guess I didn't draw. If you started 3-2, you would be going like this.
And from 2-1, I guess as well.
Yeah. So basically. This Chevalier formula, the multiplying with Schubert divisors, is exactly the same. The only difference is that you now include these. You're allowed to get to these affine roots.
And is this connected with you? I saw that there's this connection with the semi-flag varieties. Is that something?
Yeah, possibly. But I haven't been able to understand the precise connection. Yeah, this does look affine. Yeah, and I guess I also want to add that all those coefficients in those formulas are positive in the sense I talked about earlier.
General question, is it understood what is the relation between quantum K-theory and quantum cohomology in these examples?
Yeah, I think it's understood that quantum cohomology is, so there's a filtration on quantum K-theory, and the associated graded would give you quantum cohomology. So, so for example, for Grassmannian, the quantum cohomology Whitney relation would be not C1, sorry, C. And then you have a very simple term, like I think some sign times oh, sorry, this is the quotient bundle, maybe not to confuse notations. And I believe you just have some sign, and then the quantum parameter. I should have it somewhere. Let me check. Oh, maybe not here. Sorry. Yeah, I think. Let's see. Yeah, I think if I remember correctly, this is what you get in the Grassmannian case.
So are there also some analogous relationships studied in quantum cohomology science? I don't know.
Yes. So, yeah. But I think quantum cohomology is better understood. I think. So I think at least non-equivariantly, the quantum cohomology analog of the Whitney presentation should follow from a paper by Gu and Kalashnikov. Yeah.
She was at Imperial when I was there.
Oh, okay.
Student.
Yeah. That's right. Yeah, I think their paper is non-equivariant, but I think but you can. Well, maybe they didn't state it exactly in this way, but I think it can be related.
Uh-huh.
Yeah.
Thank you.
Any questions? If not, let's thank the speaker again.